Thanks for joining us today. This is another installment of the Centrify Chalk Talk series. Today we're going to be talking with Paul Moore, our CTO, about DirectSecure. It's our new product that does IPsec, and we'll be learning a lot more about how that operates with Paul. Paul, can you tell us a little bit about DirectSecure and IPsec technology? A lot of my questions when I first heard about this kind of technology was, I've heard of IPsec, but usually in the context of a VPN. So how is this different from a VPN, and what's different about it?
IPsec can operate in two modes. The first mode is something called transport mode, which is what DirectSecure uses, which is not the most common one. The one that gets used most of the time is called tunnel mode, which is what VPN uses. And that's all about taking one machine and allowing it to connect up to a network. Typically for dial-up accesses, or of course it's not dial-up anymore.
Right.
People don't even know what dial-up means anymore. But to allow you to, sitting in a hotel room, to connect to your corporate network. That's perfectly valid use, obviously, of IPsec, and it's certainly the 99% case. What we're talking about is using IPsec for transport mode, and that's all about securing traffic within your internal network to enable you to kind of do a blanket protection of your network and the data flowing on it.
Okay, so it sounds like it's a little bit more peer-to-peer machine authenticate to individual machine as opposed to machine to gateway.
Yes. Can I draw let me draw a picture. Let me draw a picture. So in tunnel mode, basically you have a dedicated box inside your network. So this is your data center here. And out here we have a cloud. And over here we have somebody with a laptop. And the laptop is connected up to the network. And then we create a virtual circuit whereby this box connects to here. And then this thing then forwards the traffic out into your main corporate network. And this is something that I said that people are familiar with, connecting to their corporate networks everywhere. But the point about it is we have a dedicated box that's acting as a front end for all the traffic. And that's not what DirectSecure is. This is the IPsec that everyone's familiar with. Or if not familiar with it, they're using it on a day-to-day basis, even if they're not aware that it's IPsec. But this is not what we're talking about. What we're talking about is the use in quite a different way, which is, I'm going to say within your data center, but in fact it can be used over a wider area as well. But let's just focus on use inside a data center. What there we're talking about is I have machine A and machine B, any two arbitrary machines, two servers talking to each other, somebody's desktop machine talking to an email server or whatever, and they're both connected to the network. And you want this traffic that's flowing between these two machines, or some portion of that traffic, to be secured via IPsec. And the things that IPsec bring for you are, so the first thing is encryption. Obviously that means the data is scrambled, it's no longer carried in plain text. That's attractive because there are still many protocols in use, especially internally within a data center, that are not encrypted on the wire. So things like FTP.
Or like an app server to database. Things like that?
Yeah, many things that are not encrypted for various reasons. But people are deciding that maybe they should have that data encrypted while in flight, even inside their data center, because it's just sensitive data and they think it's the right thing to do. Maybe there's some regulations that have changed or are going to change that would require them to do that perhaps, or it's just a best practice they feel they ought to do. The other thing you can use it for is, let's just call it protection. And by that, I mean you can control, because the packets can be signed or encrypted, the net effect you end up with is you can control, machine B can control which machines can talk to it. And that's, the difference between that and a firewall is that as we'll see later on, IPsec can act like a non-spoofable firewall. So this is, again, some hypothetical machine. What we haven't said so far, by the way, is DirectSecure is for UNIX systems. but the model I'm drawing is actually correct for both Unix and Windows systems. So we have, again, our machine A and machine B. And what I'm roughly drawing here is user space and kernel space. And typically, you'll see that the TCP stacks live down here. It varies slightly from system to system, but roughly most or all of the TCP stacks live down here. So what we're talking about is when packets are exchanged between these two machines using TCP, I said TCP, but in fact it could be IP as well, or even raw Ethernet, raw packets, like a ICMP and so on. When the packets are exchanged there, what we need to do is either encrypt them or sign them. And what that means is we need keying material to do that. Plus also, these stacks down in the base of the operating system need to know that when I talk to machine B, that I need to do the encrypt or not, and so on. So
somebody's got to define the rule set.
So there's rule sets and keying material that's needed as well. So typically there's be some kernel level portion of IPsec that lives up above this, still down in the kernel. And then up here in userland, we have something called an IC daemon. And also we have some policy management going on as well. And we'll talk about how we get that policy in the specific case. I'm just talking about kind of the generic case, first of all. So the policy management is communicating down to these things and saying, when you talk to machine B, you need to use this kind of encryption and so on. The IC daemon's job, by the way, IC stands for Internet Key Exchange. The IC daemon's job is to communicate with the far side and to create the keying material. So this guy let's say where A is initiating a conversation with B. The IC will communicate with machine B's IC daemon and will authenticate. And we'll talk a little bit more about authentication. And once they've authenticated with each other, this is the machines authenticating each other, not users. They will then establish some keying material that will be passed down to the IPsec layer, and then the TCP packets can now be encrypted or signed as required.
Great.
So that's kind of no discussion of how our software fits into this. It's just a general description of how IPsec works between two systems.
You were saying earlier that IPsec operates on we can make these decisions a little bit more like at the packet level, sounds like, as opposed to having to establish a circuit like we did with a VPN system. So does that mean it operates for individual ports? We can make these decisions independent?
So it's certainly not at a packet level. The rules are defined per port, or the rules are a combination of IP addresses and port numbers and protocols as well, so TCP versus UDP and so on. The most common configuration would be to say, everything on the FTP port needs to be encrypted. Everything on the HTTP port needs to be encrypted, but things on other ports, like the LDAP SSL port, which is going to be encrypted anyway, doesn't need to be encrypted. So you can select certain pieces of traffic which will be encrypted. You could also say that everything is encrypted. Just say all ports traffic are encrypted. And you can also say, for example, that everything should be signed, so you have the protection but not the encryption, except for the traffic that's on these ports, which also needs to be encrypted as well. So you can kind of mix and match however you like.
Because it certainly seems like at scale, if I were to scale this out to like hundreds to thousands of systems in my data center, if I choose to use it as such, it could be quite a job to manage policy across all those systems unless I had a good management infrastructure.
So that's actually one of the main reasons why transport mode IPsec, which requires the configuration of every machine in your data center that's going to take part in it, that's one of the reasons why it's not widely used, is because the management of all of that is a huge overhead.
Sure.
Whereas in the VPN case, you only have one VPN box. All the other systems in the environment are not aware of any VPN traffic going on. Sure. So you have to configure one, even though you've got 10,000 machines in your data center. Here, you have 10,000 machines in your data center. You have to configure all 10,000 of them.
But it also sounds like there's one other challenge as well, which is the policies allow you to define machine A talking to machine B and machine A talking to machine C and et cetera. Yes. So you could get into a lot of different complex policies if you wanted.
So the answer is group policy. So, and you did ask earlier on what's the situation with Windows. So first of all, reminder of what we do, which is we make software which takes advantage of all the Active Directory features that Microsoft has and make them work cross-platform. Right. So Microsoft solves this problem by using group policy. So the way that works is in a Microsoft environment, we have up here, we have an Active Directory forest, which has a whole bunch of group policies defined, and somewhere there will be a group policy which defines for this set of machines the set of rules that should be used for doing IPsec. And it's managed just like regular, it is a standard regular piece of group policy, so all the usual Microsoft rules about the scope and applicability of that policy can be done for my entire enterprise, just part of a domain, a particular group of machines, or whatever. And those rules are expressed in terms of typically subnets or specific IP addresses in combination with ports. That's the normal one, or you can have no port, in which case it applies to all ports. And so those policies...
so that means you could also have just ports and anybody talking to that particular port. Or any system, I should say.
The rule is expressed in terms of source and destination IP address, plus potentially a source and destination port number. Okay. So let's imagine we wanted to do secure FTP. We'll ignore the data port for a time being. Let's just say port 21. You would normally do source anything, source any port, destination port 21, and then you'd specify the IP addresses would be whatever scope you wanted. And obviously, you could say everything. You could say any IP address, although typically you would specify individual subnets, just in case you had labs where you didn't want things to apply and so on. So you would... Okay. So as I said, in the Microsoft environment, you define your IPsec rules via group policy, and those are disseminated to the Windows machines just as they would normally do. So the first major building block of our software is to take this set of rules and make it into policy which drives the IPsec on a, now we're definitely saying, this is, let's say, a Unix system with our software on it now. We will take that group policy and apply it to a non-Windows system. Now, what that's taking advantage of is the fact that Direct Control, which is our core product out in the marketplace for a long time, it has built-in as standard support for group policies. It understands which rules should apply to which systems and so on. So what we did was we added some extra group policy processing that reads the Microsoft group policy settings, converts those into the policy settings applicable for the machine we're running on, and then pushes those rules into the IPsec subsystem on the Unix system. Okay. So on the other side there, what we're talking to, this will also have taken the same set of rules, and this could of course be a Windows machine that we're talking to, or another Unix system with our software on it. So we have a large piece of group policy processing software, and it's not only just taking the rules as well. What it has to realize is that, okay, before I got that policy, there was no IPsec rules for me, so I don't have to activate my IPsec subsystem at all. Now, suddenly there are rules that apply to me, so now what I need to do is push the configuration down into the kernel. I have to start the IKE daemons, and I have to do all sorts of other ancillary tasks to kind of create a working system. It's not just a matter of propagating the rules. You have to kind of orchestrate all the moving parts to make sure everything comes up in a nice sequence.
But it's unlike a VPN, it seems like it's designed to operate automatically, as opposed to a user having to invoke it, turn it on.
Correct. There is no user experience. There's no administrator experience. There's no user experience at all. The whole thing, there are a few diagnostic and reporting tools just to find out if you've got some troubleshooting things. But basically, you install our software onto a Unix system. If there are rules declared in AD that require IPsec that applies to that Unix system, then automatically everything just happens. It's completely transparent to you. That's how it has to be if we want to deploy onto 10,000 systems. If you had to go and do stuff on it. So not only do you don't have to configure, it's completely invisible to everything else that's happening above. The applications don't see anything different. The users don't see anything different because all of the actual traffic encryption and validation, so when it's happening way down at the bottom of the stack, the FTP server's running up here, completely unaware of what's going on.
Sure.
That's one of the advantages of using IPsec, is that you get security, encryption, and protection and so on within your environment, but you can keep using applications that existed before anybody.
Yeah, so we're affecting it down at the network layer as opposed to up in the application layer.
Correct.
You said earlier we can protect the machine, and it sounds like we have better controls over which machines this box A or box B, would allow to communicate to that particular system. So, if I had like an app server that needed to talk to a database and wanted to protect the database, I don't really need anything else to talk to that database, just the application server. Right? So how would I define that kind of a policy?
So you can definitely say that, for example, if this is the application server, this is the database engine, you could configure this database engine. Let's suppose the database engine is running over port 123, which is typically it's got some form of reserved port. You could configure IPsec on here to say traffic coming to port 123 must have must come from other machines that I know and trust. And the way that trust is done is by authenticating those machines.
And I can define specifically which computers by a trusted name, by a trusted authentication mechanism. I assume group policy helps me with that if I'm creating, let's say, a group of computers and applying the policy based on the group, right?
Yes. I think the thing to think about first of all is you can use it very much like a firewall, which is what we're talking about there, right? You're saying, I want to make sure that if somebody's talking to port 123 on this machine, that I only want the correct machines to talk to that. And that's typically done with a firewall.
Exactly.
Right. The problem with doing that is a firewall is spoofable. Right, and I think I mentioned this before. Whereas IPsec, because we authenticate the remote side, not based on its IP address or its MAC address, but on more sophisticated technology. So let me
and you're saying it's spoofable. Firewalls are spoofable because they make decisions on IP address, MAC address as the only data input.
Correct. And those are trivial to spoof.
Yeah, I can fire up a VM on my Mac laptop.
Right. You can
define
say
the MAC
anything.
address.
Yes. Yeah. So, I mean, it's better than nothing. But if somebody's seriously trying to hit you, that's not really very secure. Whereas using IPsec is very, very secure. So let me just talk about, because I said that the first thing that happens is when the two TCP stacks decide that we need to do a protected conversation, then they will talk to the IPsec stacks, and the IPsec stacks will talk to the IKE daemons, and the IKE daemons will talk to each other to mutually authenticate each other so that machine A can be sure that it's talking to machine B, and machine B can be sure that it's actually talking to machine A. Mm-hmm. And the way the authentication works, there are three mechanisms that are commonly in use. So the first mechanism is number one, PKI. This is by far the most common one to use. In other words, using certificates to authenticate the machines. Basically, machine A and machine B will exchange certificates with each other, and the fact that they can prove not only that they've got the certificate, but they have the private key as well by sending each other challenges that they are asked to encrypt. Using the private key, and the other side decrypts it using the public key. Plus, it verifies that the certificate's issued by a place that it trusts as well, then if we pass all those hurdles, then A and B decide to trust each other. And we can talk a little bit more, because obviously there's a lot of back channel about how you get certificates, how you know who to trust, and all of that kind of stuff, which we'll come back to in a second. So the next one we use is pre-shared keys, which is kind of pretty lame. Pre-shared keys is basically passwords.
Sounds like I give you a password and you give me a password and we just simply remember them.
Yes, yes. So machine A and machine B, basically they go, the password's Rumpelstiltskin, and B goes, yep, Rumpelstiltskin. So by the fact they both know that today's magic word is Rumpelstiltskin, in fact, I say today's, in fact, a PSK is valid for the length until somebody changes it. So it's not something that changes on a daily basis. It's configured in the policy.
That sounds a lot like web keys, which people know pretty easily how to break, and given enough traffic.
Well, you can make it in, it doesn't have to be Rumpelstiltskin. It could be some very long, complicated thing. But it's certainly not as secure as it could be, because typically humans have been involved in creating it and therefore, and distributing it, and therefore it's subject to all the weaknesses that, that humans are subject to. Whereas PKI and so on have got much more sophisticated generations of secrets and so on associated with it. The reason it's there is because there are some computer systems out there that this is the only thing they support. Some of the older ones that see certificates as being incredibly sophisticated, and whereas PSK is obviously relatively straightforward, and it's better than nothing, because it still does end up encrypting the traffic on the wire, and it's better than it not being encrypted on the wire. And then the final one is Kerberos. Now, the advantage of using Kerberos as an authentication mechanism is that if you're in an AD environment, which of course is what our customer base is, then all the players in the enterprise, all the machines, I mean, already have Kerberos credentials, assuming they're all joined to the same forest, or even with cross-forest trust.
Similar to other services where machine A would just request a service ticket to access machine B and exchange the service tickets? I mean, they're not going to share their secrets or...
No. So the way it works is exactly as though this was, let's say an SSH, I was going to say exactly that, an SSH client talking to an SSH server using the Kerberos credentials, probably of the user in the SSH case, but it would be the machine in this case. So when this is a Unix system. When a Unix system is joined to the domain using our software, one of the things that happens is we'll actually end up with some Kerberos credentials here. What happens is that if machine A, remember, is the initiator talking to machine B, it will read its credentials and request from AD a service ticket for the IKE service on machine B. It then, in this communication path here, it then sends the service ticket over. There's a GSS mutual authentication takes place between the two systems. So again, we've got the same idea that machine A definitively knows that's machine B, and machine B definitively knows that that is machine A. The advantage of doing that is that, as you'll see when we talk about PKI, there's a lot more work. There's a lot more moving gears in the system for the PKI, whereas the Kerberos one, it's already done before anything else happened because you joined the domain. And of course, for a Windows system, this is our Windows partner over here, they have the same thing happening when you join the domain. The only challenge is, of course, that you might have systems that are not in the domain that you need to talk to as well, in which case then the Kerberos solution isn't appropriate.
It also sounds like, I mean, with Kerberos, you'd have to assume an online state or ability to contact your Active Directory domain controller in order to request a service ticket for
this is true.
Other machines.
This is true. The general assumption is that if machine A is talking to machine B anyway,
quote, you're online.
that you're basically online. I mean, obviously it's possible, but the classic offline case for Windows and for us is you've got a laptop and you're sitting on a plane. Right. And in that case, you're not going to be talking to machine B anyway. So, but you're correct. You are correct. There's definitely an additional machine needs to be involved in the Kerberos case. You have to go and acquire credentials for machine A to talk to machine B, whereas in the PKI case, you definitely don't need to do that. The first question is, how the heck do I get a certificate, right? Because that's a classically hard problem to solve on a large scale in many data center environments, right? Is people don't like certificates because they're difficult to manage. They're easy to issue in ones and twos by some manual process, but again, we're talking about tens of thousands of machines. Trying to get certificates issued onto those and also kept up to date and so on is very difficult. So the answer to that is Active Directory again, right? Because that's what we do, is we take the Active Directory services and make them available cross-platform. So associated with AD, it's not really part of AD, but it's certainly tightly integrated with AD, is you have a certificate server. And
this is one of those things that's how you can just install on a Windows server. It's just another role, if you will.
Yes, that's true. And originally it was just called the certificate server. Now I think it's called Active Directory Certificate Services. It's kind of
branding.
But it's a branding thing. I mean, it always has been very tightly integrated with Active Directory. I think it's just positioned as being even more so now. So the way the certificate server works is that it has associated with it, and I'm kind of simplifying it a bit here. There are things called templates. Where will I fit it in? Yes. So we have a whole bunch of certificate templates, which are named. So the certificate server knows that if somebody asks for a certificate for a machine, let's say, there will be a template called machine certificate, and it will say it has to have this kind of key with this many bits and is valid for this long, and this information needs to be contained in it. Whereas if somebody asks for a certificate for something else, it's got whatever different characteristics. Sure. So in general, all that needs to be filled out is the name of the principal. So if it's a machine, you just need to fill it. The only piece of blank information that needs to be filled in is the machine ID, or in the user case, the user name needs to be filled out. The rest of it's kind of pre-filled out in that template. The certificate server has an RPC interface, which it uses to communicate. I'll take that K out of the way. Which it uses to accept requests to issue certificates from the network.
Okay, it sounds like another method of accessing the registration authority interface. Some other PKI infrastructures call it a registration authority that does registration functions and separate from signing.
All I know is that if you want a certificate from this guy here, you use his RPC interface and he'll give you a certificate.
And the only interface I've seen is the HTTP interface, because.
Okay, so that's for GUI. That's for people to use. And then the question is, of course, what does the web server actually use? Because the web server itself that you're in the HTTP interface is a web server. It's not a certificate server. So in fact, the web server is just a front end to this interface as well.
Okay.
Everybody ends up using this interface. That's not strictly true. There are a few other ways in, and in the latest versions of Windows, they've added a few more ways. But this is still the kind of 90% case. So the other thing we have is, and I'm sorry it's getting a little bit complicated over here, there are also group policies associated with the certificate server. So there's a group policy which controls whether machines or users should have certificates automatically issued to them. So there's a group policy which applies down here and also applies to the machines themselves, saying, or users. But we'll focus on machines, because remember what we're talking about here is PKI credentials for machines to identify themselves to other machines. So the certificate we're going to use will be one that identifies the machine. It's associated with the computer. So there's group policies which define which templates the certificate server should use, and also whether the machines should request certificates or not. So up here, this is another piece of software from us. We have a certificate requester here, which will communicate with here and is driven by group policy. But I'm not going to draw that because that's too much. So this little component here is responsible for knowing that the group policy is written that applies to it, to say, if you must have a certificate on this system, you must have an up-to-date certificate. And what that policy will then do is look in its certificate store. So we have a little certificate store here. Store. And see, well, do I already have a certificate? If not, or if my certificate is expired or about to expire, then it will go and talk to the certificate server to request a certificate. And it will use the correct template out of the template store. It will tell the certificate server, I want the one for machines in this environment. Okay. The question you're asking me, I can see the look in your eye, which is, how does this guy know that this guy is, I mean, he doesn't want to give certificates just to any person that claiming to be machine A. Right. So what it does is, in fact, it uses the same mechanism we talked about before, is that it uses the machine's credentials to request a certificate from the certificate server. So it does a Kerberos communication, and again, that's a mutually authenticated communication, so the certificate server definitely knows this is machine A, and it doesn't even ask it what its name is. By looking at the Kerberos credentials, it knows to issue a certificate for machine A. So it returns it all the way back and puts it in here.
So it all starts with the join to Active Directory.
Yes.
We join AD, we pick up some policies. I would assume the next thing is the cert infrastructure sees the policy for, I need to have good certificates, and it says my store is empty, I go authenticate with Kerberos and pick up a certificate.
Yes.
And at that point, once I pick up the group policy for IPsec, then things can work correctly.
Yes. And in fact, so what happens is if you have both direct control and DirectSecure installed on the same box, when you do a join, the credentials are created, and then when, for the first time, direct control fires up, all the policies under the hood will all run to make all this happen. And the next thing you will see is all of this infrastructure fires up with the correct service certificates and the correct policies in place, and so on.
So it sounds like I really need to protect my process for joining new machines if I were to prevent a rogue system from coming into the environment.
In a typical environment, you need to be a domain administrator to join. That's not strictly true, but obviously varies from enterprise to enterprise. But typically, you need to be protected to do that. Sorry, you need to be privileged to do that.
Do you use IPsec to protect the Active Directory infrastructure, or
no?
Do you have to leave that one open?
There's a kind of bootstrap. There's a bootstrap issue here because we can't. When we first talk to it, we don't have the capability of talking IPsec to it because we don't know what the policy is. We don't have certificates and so on. So, in a typical deployment, again, the actual traffic to the domain controllers themselves is usually excluded from the IPsec traffic. One of the interesting things about the PKI infrastructure here is that it's actually completely independent of the IPsec infrastructure. So obviously, we've created it to enable the IPsec infrastructure, but it's usable on its own. So if people have got other mechanisms that require certificates, so for example, they have web servers, obviously one of the classical uses of certificates, it just creates a certificate store, just like on a Windows system. If you say, all my Windows servers must have machine certificates and they'll be put in a standard certificate store, we do exactly the same thing. So now any application that wants to take advantage of the machine certificate can do it. So 802.1x port level things, web server, or anything that needs to be protected.
You just have to configure it to look at for the certificate store where we put it.
Yes, yes.
So in that case, there's probably one more arrow that needs to go into the Ike daemon, is that right, from the cert store, so that Ike daemon gets to use
exactly so. Exactly so. There you go. But what about trusting the certificates? So we've issued certificates, but that doesn't resolve the case of trusting it. So the whole thing about a certificate is two things. A certificate is really just a bunch of information about a public key, right? That's really what it's about. And the owner of a certificate must have the private key for that that goes with it. I can give you my certificate.
Well, that's because during the key generation process, we generated a private key, public key pair local to the machine A, yes. Submitted public key, and he took that along with some additional information, created my certificate out of it.
Yes, yes. And I can present you with this certificate, and I can prove to you that I've got a private key that goes with it. But that doesn't mean anything to you, because if you don't know where that certificate came from in the first place, you don't know that it's a trustable piece of information. So there's two things I have to do to show, for you to be able to trust me based on certificate exchange. The first one is I have to show you that I actually have the private key. And the second thing is you have to trust the person that's issued the certificate, right? And in this case, again, we've been focusing on this guy. So in a certificate exchange, we mutually authenticate each other's certificates. That I trust your certificate, and he's obviously going to do the same thing to trust that you trust mine. The solution is you have to have the certificates associated with the issuer of the certificate. So if you look at a certificate, of course, doesn't look like that really, but we'll draw it like that. It has all sorts of information, and one of the things it'll have is the issuer. And I'm sorry if I'm, this is kind of crypto 101, certificates 101. But basically, one of the pieces of information in a certificate is typically the name of the certificate authority that issued it. And in this environment, it would be some sort of name associated with this guy or the forest or something like this. If this is acme.com, it would be the certificate of ca.acme.com or something like that. What we would need to do then is we need to get the certificate associated with the issuer and install them in the certificate store here and on this guy, so that by having that root certificate installed on those machines, then I can see that that certificate was issued, and I then know to trust it because it was issued by somebody I've been told to trust.
So we need to update the list of trusted root certificates.
Yes.
On this machine.
It took me a bit of a mouthful to get that out, but that's basically correct. And of course, to the rescue comes Microsoft and group policy. And so they have, inside GP, there is a whole bunch of root certs.
So is this different than the, we have other products that on the Macintosh side that do smart card login, and I thought we leveraged a different repository of trusted roots that actually came out of Active Directory.
There's a lot of different root certs that's kind of spread all over the place within AD. The ones for smart card login are very specific because AD has to be told specifically when it's doing smart card issuing, these are the root certs for doing smart card issuing. And they're in a separate place because they're even more special than the general ones because they're used by AD itself to issue, to decide what it personally trusts as opposed to just being the housekeeper for anybody trusting things out there. It's even more fussy about that. So there's a very specific store. For the general trusted root certs within the enterprise, there's other stores. So we actually, in this case, pull out multiple root certs from various stores, including the smart card focused one, just to make sure we get everything and store them in there. So as part of this group policy processing, we do that. And then that means now that we know who we should trust and who we should not trust.
Okay. If we have the mechanism to validate PKI credentials and prove that it came from a trusted authority, it's not been revoked, assume we have all the capabilities of processing non-revoked, CRL processing.
I was just going to say, there's a lot of moving parts in the AD environment as well, but we already Microsoft solved that, when Windows 2000 shipped, and we've solved that over the 4 or 5 years that Direct Control's been in the marketplace. So those, we see those as completely non-issues. In fact, there are a lot of moving parts, just we already fixed that. Here in PKI, there's another set of moving parts which needs to be. And what we've tried to do, and I think we've actually succeeded, is to make it operate as smoothly as joining AD does. We automatically go and get everything, we automatically check things, and automatically keep things up to date. We made it so that it's really dull and boring to deploy what's actually quite a complicated piece of technology. And yes, we do have CRLs are stored also in the certificate server, and we have code actually here to go and manage CRLs, and you mentioned OCSP to deal with that as well, and that's all to do with certificate revocation. Okay. So one of the major things we did was we did a huge amount of work, an enormous amount of work, to the existing daemon code on Unix and Solaris. And that I'd like to cover as a kind of separate topic, because that's actually, it's digging a little deeper, and it may be interesting to people, you know, slightly different people might be interested in that.
But it sounds like what was present in the current set of OSs worked, potentially worked for VPNs, but didn't work in this particular mode. Is that
absolutely? So for Windows, obviously it worked in transport mode as well. But in Unix, it's very true that the transport mode of operation, what we've seen by looking at what the knowledge out in the environment, you know, on the forums and internet and so on, plus looking at the code, it's clear that those code pathways are not very heavily exercised. VPN works fine, but the transport mode requirements, and also some of the more sophisticated PKI requirements, which you do need in a large-scale enterprise deployment, and those things were just not present, or certainly not reliable. Yeah, so yeah, that was one of the major pieces of effort was fixing this on various platforms.
Back to one of the first things I was trying to understand a little better. If I have a group of machines defined within an Active Directory group in AD, how can I make sure that those machines would only accept traffic from that particular group, yes, and nobody else, based on name, not IP address?
So it's a usage model of being able to control which machines can talk to a given machine. So I can be able to say, for example, for machine B, only these other machines can talk to it. Now, typically the way that's done, again, is firewalling, right? Which is typically associated with specific IP addresses or ranges of IP addresses. The problem with that is it's very tightly coupled to your machine, to your network infrastructure, and if the network doesn't kind of split up like that or things move around, it doesn't work very, very well. What's better is if somehow you can use a higher level logical grouping of things, for example, AD groups. So, and I suspect this was kind of an accidental discovery by Microsoft. They suddenly realized that they have quite a powerful tool at their disposal. And I don't know if this is the case, but it looks like an accidental discovery to me. So on a given Windows machine, and I'll talk about how you do it in the Unix environment in a minute. On a given Windows machine, you can say which principals, and a principal can be can be a machine or a user within the AD environment, which principals are allowed to locally log on, and which principals can remotely authenticate. And typically that's on a secure box, you want to say only members of the domain admins group can log on locally to this machine. You know, right, on one of my mission critical servers. You don't just want any old person logging on to some of my mission critical machines. However, if you think about doing a Kerberos authentication, machine A authenticating to machine B, what's actually happening within the Kerberos layers on the Windows system is machine A is actually logging on remotely to machine B. That's actually what's happening. Mm-hmm. So if you have and again, this is controlled by a group policy. You have a group policy set over here that says grant remote login rights only to members of group X. Then machine A must be a member of group X for that Kerberos authentication to work. And if it can't do a Kerberos authentication to the IPE daemon, it can't do the IPsec traffic. And therefore, if this machine is configured to only allow IPsec traffic, then effectively machine A is blocked. Only members of group X can communicate to machine B. Which, as I said, I'm not sure if that was I suspect that wasn't the original design intent there, but it's actually a very useful feature. And in fact, it works. This is where this digital signing works, right? Maybe you don't want the traffic to be encrypted, but by requiring it to be signed, you still have to have had a successful IPsec handshake between the two machines for them to be able to exchange. And this is another example of this, of treating it like a next-gen firewall, because now we've not only got rules that are unspoofable, but you can specify the rules in terms of high-level abstractions, like what groups you're a member of, as opposed to what IP address you are, which makes it much more flexible and really quite useful in an environment.
So, just real quickly on the Kerberos side of things, who's doing the enforcement of that? Is it the destination machine?
It's here. It's here. Yes.
So Active Directory domain controller didn't say, oh, you can't, so he'll still give you back a service ticket.
Yes, so I ask for a service, yes, it happens here. So what happens is I ask for a service ticket, and this software here will say you don't have remote authenticate permission to do that. Where AD is playing part of that is typically, although it's not necessary, is the rule over here saying which users or groups of machines have remote authenticate permission is typically defined in group policy. Okay. Yet another thing defining group, although it doesn't have to be. You can define that locally, just in a local registry configuration to say only these people have remote rights onto that system. Of course, you have to make sure that you include the right people, because once you start specifying who has remote rights, you can't just say only machines in group X can do it, because then that means no human can authenticate to it. So you do actually need to include in there the users that are going to authenticate to it remotely as well, once you turn that on. So we implemented that. So you can do exactly the same thing on the Unix side now. So we have we read the same policy, which groups are allowed to authenticate remotely, and use that to enforce the IPE authentication. Okay. There's also in PKI the same kind of thing happens. Now, because this is when you do a PKI exchange, that's not seen by the authentication infrastructure on the Windows side. Right? It's not actually a remote sign-on. It's just happening at the way up at the application layer. They're just exchanging packets with each other.
And that's because they're able to validate the certificates without going and asking the authentication subsystem?
Exactly. So what Microsoft has done, and we've done the same thing, is they do a mapping down in the IPsec layer to look at the PKI certificate and work out which machine that is and map that to a machine in AD and do the same check to make sure that that machine is in the groups, okay, if there is a group specified. So if you look in the Windows policy UI, you'll see a thing saying enable certificate mapping. It's not obvious what that does, but what it means is the blocking access via groups or not is for PKI authentication. You have to check that on, and then the same mechanism happens. And again, we have the same thing implemented over here.
Okay.
There's actually multiple different things of policies you need to set up to make all of these bits work correctly. You have to define the IPsec rules themselves. You have to set up, if you're going to use PKI, you have to create all the policies to control the certificate templates and the auto issuance. You have to set up the root certificates. Plus, if you want to use that grouping of machines to create trust between them, you have to use the centralized policy for doing that.
But it sounds like I could very easily go back and define for my really sensitive servers, require them to get PKI certificates, require anybody that talks to me, if I'm a sensitive server, anybody that talks to me has to authenticate, and for specific ports, I require encryption, and then go back and define another policy that says I'm only going to allow machines that are a member of this particular group in order to communicate. Yes. So that really tightly locks down, yes, who can communicate to that system. Yes.
But be careful. Be careful with the force, Luke. This is a very powerful tool here, right? That it's possible. You shouldn't just willy-nilly apply policies, because it's possible to lock yourself out. That's one of the challenges. So you must always be careful with this, because if you manage to configure IPsec in such a way that nothing can talk to it, you now can't get in over the network and change your mind.
Yeah, there sounds like there's a lot of other use cases where it may be valuable as well, even across the wide area network. I mean, I've heard of people needing to have machines that are, quote, in a department, but they're one's on one side of the wide area network and one's on the other side, and trying to do this with older technologies just would have been really difficult.
Yes, this definitely makes it easier to make sure your traffic's encrypted everywhere, definitely.
Well, thank you, Paul. Thanks for joining us today, and thanks for joining us for this Chalk Talk on DirectSecure. We hope you learned a lot about DirectSecure today and IPsec and how the underlying functions work. Please join us for a few other Chalk Talks you'll find available on our website.